Okay, now let's extend our discussion a little bit further. So far, we are talking about linear regression. That means you want to draw a line through the point that best actually represent the trend of the data. So this is a linear line. We are actually plotting a line, just a single line. Okay. Now the equation that we get for finally last time, that was like n a naught plus summation of xi, this was a1, is equals to summation of yi. Okay. Then we had summation of xi a naught. This was after the derivation. It is given in the book. Summation of xi square a1, that is equals to summation of xi and yi. So from the representation, you can actually see that we can easily take it in a matrix form. If we take this portion and this portion and this portion in a matrix form, we can put a matrix like this: n, then there is this summation of xi, there is this summation of xi, and there is this summation of xi square, right? Then we have a naught, that was the first term, and a1, that is the second term, and that is equals to summation of yi divided by summation of xi and yi. So this is a matrix. So we can name it as, say for example, a, no, not a, it's already there. Let's name it as c. This is our theta. A means theta, that was already represented. C theta is equals to, that is our d. Then a normal way to solve it would be just to take the inverse of it, c inverse d. Okay, let's first check that whether it works or not. Okay. So first we had our x and y. We check here, x was 1 to 7, and y was a vector of length 7. So we can make our c vector, that was, first comes 7, that was n, then summation of x, okay, then go to the next line, and again summation of x, okay, comma, then summation of xi square, that means summation of x square, and I have to use this one. Okay. So this is our c. This is our c matrix. Okay. Then comes our d matrix, that was equals to summation of y, then next line summation of xy, that means x dot multiplication of y. Okay, so let's see. So this is d. Now if I want our theta, so I have to take the inverse of the matrix. Now, so if I write theta is equals to inverse of c multiplication by d. If I run it, as you can see, the theta is actually appearing 0.0714 and 0.8393, and I believe that was our answer, 0.0714, 0.8393. So that means this inversion is working. But the problem is, in matrix we actually try to avoid this kind of matrix inversion. Okay. There are long discussion regarding this, because you remember the determinant, when you are actually performing this kind of inversion, the determinant goes in the denominator. So there is a numerical overflow related things. So we are not going to discuss that. So basic idea is we actually try to avoid this kind of inversion. So in order to do that, what we do, we actually use gradient descent algorithm. That is the most suitable algorithm, but it is not actually discussed in your lecture, so I am not discussing it here again. This is for your normal task. Okay, just understand. Now if we extend this one, see if the data looks like this. Now if the data looks something like this, so what is or how should I plot, how should I actually understand the trend of the data? It actually quite looks something like this. Should I go like this way? So this is the trend. Now again, understand, sometimes when you have a small amount of data, the trend may not be accurately visible. Okay, we're assuming from the data that it is the trend, but this is not a natural occurring scenario. That why the trend should be like this, okay, based on the x variable. The best way is to actually get more data. Get more data. Whenever you are trying to make something like this, a trend in the data, you need at least a decent amount of data. Previously, I was just showing with 7 examples. Normally, we actually want more data so that we can understand the pattern. What is the pattern of the data? So, for example, here you can see this is one line. There is another point. Should we consider it as an outlier, or should we actually think this should be the data? But we are not sure. But if we actually feed more data into there, then we'll see something like this. Let's remove these portions. This one. Okay, so say this was the original data that you collected, but when you collect more data, you are seeing the data actually something like this. You are getting some here, but now the trend is like this. So how do we? So if you look at here, so data actually looks more like this. The shape is more like this instead of a shape like this. Instead of a shape like this, the data is actually more like this, and this is more likely to be a trend in the data. That is a better trend than this kind of fluctuating shape. So this actually represents a better trend in the data. And more important, and moreover, this is actually not a linear line. So far we have actually talked about linear line. We are fitting a linear line in the data, but the line can also be a curve like this. Okay, a curve like this. It can be a curve like this. Okay, any kind of curve can be there. So how do we actually do that? So in order to do that, so far we are actually fitting a linear line. Say for example, y is equals to theta naught plus theta 1 into x. That is a equation of a line. So what if we try to increase the polynomial order? So theta 0, say let's keep it here, theta 0 plus theta 1 x plus theta 2, this is the theta 2 plus x square. That means I'm trying to fit a higher order polynomial here. So let's see how the curve looks like. What I want to plot, let's say plot x comma, previously we are trying to plot theta 0 plus theta 1 multiplied by x, right? So this is our original plot. Okay, so in MATLAB, the problem is in MATLAB the index starts with 1, not 0. Okay, so if we try to plot it here now, okay, so this is the line. Okay, this is the line that we're actually trying to draw last time. Now let's try to fit a polynomial here. We have not actually yet identified the values of these things right now. Just trying to see how the curve should look like. Okay, that is comma. Let's keep it as this. Plus, let's say let's fit this arbitrary value 0.7 multiplied by x square. Okay. As you can see, the curve now looks like this. Okay, I have a bend shape. So if we increase the polynomial, the curve would look like this. Okay, if we increase it even further, say for example 0.34 multiplied by x dot to the power 4. Let's see how the curve looks like now. As you can see, there is let's here. The curve, if you look here, the curve is now this way. So it is like this way. That means there is a kind of overfitting is happening. Okay, this is not a pure straight curve. As we increase the order of the polynomial, the curve will be like this. So if you look at the data, that means what is actually happening here, the curve is fitted like this way. Okay, the curve is fitted like this way, not a pure shape, but the shape would change like this, and we do not want this way. That means actually when you're increasing the order of the polynomial, you are overfitting your data. Okay, you are overfitting your data. It's called overfitting. This is like overfitting. That was the first thing we actually discussed. When you have a data like this, if you have points like this, if you connect the points this way, so this is also one type of curve fitting, but that is not the trend of the data. Okay, when you start to increase the order of the polynomial, it will actually tend to fit the curve like this way. It will actually tend to fit the curve like this way, but we don't want. Don't want to do it this way. Rather, we want the curve to look like something like this, something like this. Okay, so when you're increasing the order of the polynomial, you have to be very careful that don't increase the polynomial too much, because that will overfit the data. So keep it with 2 or 3. So how do you understand which order of polynomial should be better fitted, more suitable for your data? You have to visualize the trend. You have to visualize the data. First, you need to just plot a scatter plot. A scatter plot of x comma y. First, plot the data. See how the orientation of the data, how the orientation of the data is. Then decide which thing do you need. Do you need a linear line or do you need a curved line like this? Okay, so based on that, you actually decide that okay, I need a polynomial here or I need a linear line here. Okay, now how do we solve when you have a polynomial data like this? Again, as if you look at your lab manual, so this is the these are the set of equation. Again, as you can see, a0, a1, a2, you can again put a matrix like this. You can put a matrix like this. Okay, and this should be your a0, a1 and a2, and that should be your there are 3 matrices, okay, y1, y2, y3. Okay, if you inverse it, you will again get the values of a0, a1 and a2. Very simple, the same way that was shown in the last one. One last thing that I want to talk about, that is actually the original example. In the original example, here we actually plot in the y-axis we had price, in the x-axis we had number of rooms, and with like I said that with number of rooms we can actually better understand the price completely, because there are some other variables included. For example, what are the number, how many bathrooms are there? Is it a 1 bathroom house or it is a 3 bathroom? Okay. How is the view? Okay, how is the view? Or again, how is the size of the house? For example, square feet. It can have 3 rooms, but the rooms can be very small. So you also want to know what is the square feet, what is the total area of the house. Then again, whether it is in the 3rd floor, whether it is in the 1st floor, whether it is in the 6th floor. If it is 1st floor, obviously the price would go down. Okay, 3, 4, 3rd floor is more actually attractive. So there are some other parameters or variables. We call them attributes. Okay, so instead of so if you want to consider these attributes, you can also you can actually create a much better estimation. You can actually put forward a much better estimation if you actually consider this attribute, this attribute, this attribute. Okay, so how do you do that in a single line? How do you make a linear regression model with multiple features? Okay, attributes or features. Okay, this is called actually multivariate linear regression. It's called multivariate linear regression. Okay. In multivariate linear regression, so the equation would look very simple. That was your original equation, theta 0 plus that was theta 1 into x1. x1 was your first feature, say for example number of rooms, and theta 1 was the coefficient of that, plus theta 2 into x2, theta 2 into x2. So this x2 is something like this. This is your second feature and this is its coefficient. Then say for example theta 3 x3, this is the 3rd feature, it is the 3rd coefficient, 3rd feature and the 3rd coefficient. You can also have something like this, theta 4 x2 x3. You can add the multiplication of the 2 feature and create a new variable from it. You can also make it like this way. So this will actually create a multivariate linear regression model. When you have something like this, say when you have 2 features, so that means you are in the 3 dimension now. So you are no longer in the 2 dimension. When you have 3 features, you have 3 dimensional now. So with this line, you are actually trying to plot a surface like this in a 3 dimensional plane. In the 3 dimensional plane, you are trying to fit